Alright, we're going to be talking about correlation in this video. A scatter plot displays the direction, form, and strength of a relationship between two quantitative variables. When the association between two quantitative variables is linear, you can use the correlation to help describe both the strength and the direction of that association. We use R as the abbreviation for correlation. We do not use C, we use R. Now, here's a big caution. It's only appropriate to use correlation to describe strength and direction of a linear relationship. So if you're looking at the scatter plot and it doesn't look linear, do not use correlation to figure it out. Okay, here's for our definition. Correlation measures the strength and direction of the linear relationship between two quantitative variables. Some facts that are true. It is a number between -1 and 1. So this was earlier when I was saying when you're describing the scatter plot, don't say there's a, the correlation, blah, 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 because correlation is a number. It's a number between -1 and 1, so it's usually decimal. When R, this correlation, is positive, above 0, then there's a positive association. When it's below 0, there's a negative association. The strength of the linear relationship increases as R moves away from 0 towards -1 or +1. The only time R is going to equal 1 or -1 is going to be in the case of a perfect linear relationship. So unless it makes a perfectly straight line, it's not going to be exactly 1 or -1. Now, correlation is not the slope. Correlation is not slope. So you can have two lines or two sets of data that have different steepnesses, but they can have the same correlation because of how strongly they resemble a line. So again, correlation is not slope. It is the direction that the line is going and the strength of that linear relationship. I should say not the direction of the line, but the direction the data is trending. Now, there is a formula, as with all things. Isn't she lovely? Ooh. Now, this is on the formula sheet, but the chances of you actually needing the formula is very, very small, and I will show you how to do this in the calculator as well. But I want you to think about what it represents. You can think about this formula as being the average of the standardized scores, aka the z-scores of x and y. So if you recall, to find a z-score, you take x minus the mean divided by the standard deviation. So each x value minus the mean of the x's divided by the standard deviation of the x's. And then each y value minus the mean of the y's, right, y hat, or y bar, excuse me, divided by the standard deviation of the y's. And then we're adding them all up and dividing by n minus 1, so it's kind of like the average of those. Okay. Here are some different visuals that shows you different values of the correlation. So when R is 0, you can see that there's no association, there's no direction, and there is no linear strength. As it moves further from 0, you see more of a pattern until it gets really close to either 1 or -1. So those are just some examples. All right, this is not like a really hard and fast rule, but students are always wondering, like, when do I say this? When do I say that? So I made this chart. This is not, College Board approved as far as like this is what you say when, but this can be a helpful thing if you're unsure of how to describe R. So if your R is -1 or +1, you know it's perfectly linear in that direction. I say something is strong if it's 0.75 or bigger, or -0.75 or smaller. If it's around 0.5, positive or negative, it's about a moderate relationship. Around 0.25, we'd say weak. And then 0, there is no linear relationship. Again, this is not hard and fast, but this can be helpful for knowing what to describe when. Some facts about the cautions about correlation. Actually, these are just facts. Cautions are on the next one. The explanatory and the response variables do not matter in the correlation calculation. Fun fact. So if you look back at, If you look back at the formula, it wouldn't matter if I switched x and y because you're multiplying them together and then adding them. So if you said the explanatory was actually the response and vice versa, you would still get the same value of R. Okay? So the explanatory and response values do not matter in the correlation calculation. Now, because R uses those standardized values, right, those z-scores, it's not going to change when the data is transformed because it's been standardized. Okay? So for instance, like if your data was measuring like height in centimeters versus weight in pounds, and you converted it to height in inches and weight in, I don't know, kilograms, that's a unit of measurement, it wouldn't change the value of R. It wouldn't change the strength and the direction of the linear relationship. R actually has no units of measurement, so you wouldn't say it's like R centimeters or R pounds. It's just whatever the value is. You can only calculate it if you have quantitative variables, 2 quantitative variables, so you can't do this with categorical data. You can't do it with only 1 quantitative variable. You need 2. And again, correlation measures the strength of linear relationships, so do not calculate correlation if you know that it's not linear. And then finally, it's not a complete data summary. You would want to do other things in addition to calculating R, which we'll talk about later in this unit. Like I said, R ignores the distinction between X and Y. So you can see 2 scatter plots here, miles on the X, price on the Y, and then vice versa. It's still going to have the same direction and the same strength, so it's going to have the same value of R. R is affected highly by your outliers. So you can see in this first scatter plot, we have an outlier present here, and the value of the correlation is only 0.4. If you remove that, it's going to look much more linear, and then increases the strength to be 0.7. So it goes from like a moderate to, or like a somewhat moderate to like a moderately strong relationship. Like I said, since R is calculated using standardized values, the correlation doesn't change if the units of measurements are changed. So also adding a constant to either X or Y will not change the correlation because neither the standard deviation nor the distance from the mean will be impacted. Okay, so it doesn't matter if you're transforming that way. A couple of cautions about correlation. Correlation does not imply causation. I've said this once, I'll say it again. Just because your correlation is like 0.99 does not mean that your explanatory caused your response variable. Also, correlation does not measure form. So even if you were to calculate the correlation of a set of data and it was strong, that doesn't necessarily mean that it is linear. A perfect example of this is if you were to take data that was quadratic in nature, right, kind of looked like a parabola, and you only looked at the first couple of data points, so maybe like 0, 0, 1, 1, 2, 4, and maybe what's comes after that, 3, 9. The correlation coefficient R would be pretty strong, but we know that that's not linear, so be careful there. Correlation should only be used to describe linear relationships, as I said. And also, it's not a resistant measure of strength. So as you saw in that earlier one, the outliers can have it will have an effect on the strength. If you were interested in learning more about the formula, you can pause this and read it here. There's also more in your textbook. I'm not super interested in this, but if you want to learn more, here's this for you. All right, let's do some practice. We're going to describe and interpret the scatter plot, making sure to estimate the correlation. So my first picture, my first scatter plot, is showing the number of boats registered in the thousands compared to the number of manatees killed by the boats. So we're going to describe and interpret the scatter plot. So we're going to go through our DUFs. As the number of boats registered in Florida increases, so does the number of manatees killed by boats. Notice how I didn't say this caused the other, but I'm just saying what I'm seeing in the picture. This relationship is evident in the scatter plot by a strong, positive, linear relationship. So there were no unusual features that seemed here. I used my context, the strength, the direction, and the form. A good estimate here I'd say is about 0.85. Any estimate between 0.75 and 0.95 would be acceptable. All right, let's look at the next one. Describe and interpret the scatter plot. We're looking at number of storms predicted versus storms observed. I mean, I can kind of see a positive relationship, but it's super weak. I guess you could call it linear, but it's going to be a very low value of R. So as the number of predicted storms increases, so does the number of observed storms, but the relationship is weak. Yeah. Fairly weak, positive linear relationship. If I had to estimate it, I'd say it's about 0.25. If you estimate anything between 0.15 and 0.45, that would probably be a good estimate. If you're given the raw data and you wanted to calculate R, here's how you would do it in your calculator. So at this point, if you don't already have your calculator out in front of you, let's do the calculation together. So we're looking at this data that we've been dealing with about body weight and backpack weight. Go ahead and put the body weight in your list 1 and the backpack weight in list 2. I do not have that data up here in the visuals, but it is down here. So take a time and do that. You're going to go, after you do your list, exit out, go back to Stat, go to Tests, and go to the option that says Lin Reg T Test. Depending on your version of the calculator, it's either letter E or letter F. Most calculators are probably E. You're going to have your explanatory in list 1, your response in list 2. Ignore everything else, and then go down here and you click Calculate. It's going to give you this nice long screen. You need to scroll down, and the very final value they give you is R. So for this data, you should get an R value of 0.79. So go ahead and pause this video if you need to, and make sure you can calculate R given a set of data. All right, go ahead and pause this video, and I want you to work on these 2 examples. When you're done, you can unpause and hear the responses and see if they make sense for you. So we have a scatter plot here. It shows the relationship in the years between 1900 and the 100-meter sprint. Describe the relationship, and then if this is R, I need you to interpret it. As far as describing the relationship, there's a fairly strong negative linear relationship between 1900 and the 100-meter sprint record time. The runner who had a 9.58 right down here performance in 2009 is going to be an unusual point. That's actually Bolt, right? You've seen Bolt. If you ignore this, you can see how it's linear. Otherwise, you might be like, oh, Ms. Miller, it's curved. But if you ignore this, you can see how it is a pretty strong linear relationship. With an R value of negative 0.927, that means it's confirming the fact that there is a linear association, and it is negative as well. Strong and negative on this value. Next example about computer science majors. Will playing lots of video games make you more likely? No. Even though there's a really strong correlation between these 2 things, causation cannot be inferred, right? It may be that both these variables are changing due to another variable, maybe like overall progress of technology. Okay, so correlation does not equal causation. And then what effect would it have if you change this? Or does this year? What effect does that certain year have on the correlation? So that point is encouraging the fact that there's a positive linear pattern, and it makes your correlation closer to 1 because it's encouraging that positive pattern. We have arm span versus height. It's incorrect to say that correlation is 0.902 centimeters because it's standardized values and it doesn't have units. What would happen if it was changed? Correlation would stay the exact same because it's calculated using standardized values, so the changes of unit don't affect the correlation. And then finally, what would happen to the correlation if we switch them? Again, it would stay the same because the correlation doesn't make a distinction between the explanatory and the response variables. All right, that sums up our section on scatter plots and correlation. Make sure you're understanding these, 6 learning targets. There's more examples and problems in the textbook, so make sure you're doing that. Come to class with any questions. Thanks, guys.